Welcome back. So, our goal here is to get our enemies moving around and being active and being controlled by AI. Now, we know that they're currently associated with a behavior tree. If we go to our blueprints folder, go to AI, we have a behavior tree. Now, the behavior tree has a root node, and from the root node, we can attach something. We can attach children to nodes in our behavior tree. Now, one of the fundamental nodes that you can have in the behavior tree is the selector node. A selector node has the very specific quality that it will execute its children from left to right. And by children, I mean I can drag off of the bottom of my selector and put nodes. We know what tasks do. We've seen the play animation task node, and there are a number of other built-in tasks, such as wait, and other things such as move to. So these are tasks which perform some kind of action. Now, when we have things connected to the bottom of a selector, we say that these nodes are children of the selector, and the selector will execute them left to right, one at a time. Now, it doesn't just do this all at the same time, but one after the other. In other words, it's going to use this play animation node, and it's going to stop. It'll be held up here until the play animation node finishes, at which point it will then go to the next node, and once that node has finished, it will then go to the next node. Now, nodes in a behavior tree have the concept of success or failure, and whether a node succeeds or fails depends on the node and how it defines success or failure. Now, if a node succeeds or fails, it returns that success or failure information back to its parent, and the parent will then decide what to do with that information. A selector specifically has the quality that it will execute its children one after the other until one of its children succeeds, at which point it will then return success up to its parent. Now, once success returns to the root, then the whole tree starts over. So a selector with 3 children like this will execute its first child first, and if that child succeeds, it'll never get to the other children. And once it returns success to the root and starts over, if it succeeds again, then once again, we will never try to execute the other 2 child nodes. It will only ever keep executing the first node as long as it keeps succeeding. As soon as it fails, though, then the selector will try to execute the next of its child nodes and continue the process from there. So that's the behavior of a selector. Now, selectors can have things attached to them. We call a selector a composite node, and we can attach certain types of nodes to composite nodes and tasks. One of these types of nodes that I'd like to attach to my selector is called a service. Now, I can right-click on my selector, and notice that we can add decorators and services. Decorators can be attached to nodes, and services can be attached to nodes. Notice that there are a number of different types of decorators, and we'll get to decorators in more detail later, but I'd like to add a service. And a service, once attached to a node such as a selector, will execute at its defined frequency as long as the branch is being executed. Now, this selector is considered a branch, and even if it has multiple children connected to it, we consider the selector and all of its children to be a branch. If this branch is being executed, then any services attached to it will be executed, and services execute at a frequency that we specify. They have their own tick functionality. But generally in behavior trees, we don't often have things tick every single frame of the game, like your typical tick function. We tick every so often, every half second, every quarter second. We specify how often our services can tick. Now, if I wanted to attach a service on here, I could, or I can create my own. And that's what I'd like to do, is create my own service that will do exactly what I tell it to do every time it ticks. And for that, we need a new class. Now, we can make a new service blueprint, or we could make a new service C++ class. I'm going to make a C++ class. Looks like I have my project settings open. I'm going to close that, and I'm going to go ahead and go to my C++ classes, go to Aura, Public, and AI. And here in my AI folder, I'm going to create a new service. So I'm going to right-click, New C++ class, go to All Classes, and the class that I want to base this on is BT service underscore blueprint base. This is the base class. I'm going to go ahead and click Next. And this is going to be called BT service underscore something, right? Now, what do we want our service to do? Well, something I think is kind of necessary for the AI in this project is that it needs to find a player to pursue, to attack. And what I'd like it to do is get all of the player-controlled characters and find the nearest player so that it can go and attack that player. So I'm going to call this BT service underscore find nearest player and click Create Class. Now I'm going to close the editor and go into my new task. I'm going to go ahead and save selected, and let's go into our public folder, into AI, and open my new service, BT service find nearest player, and I'll go ahead and get my CPP file open as well, and here we have it. Now, as we've discussed, services tick. They tick at the frequency we choose, so we're going to override their tick function. Now, the function we're going to override is going to be protected. So we're going to add a protected section and override virtual void. The function is called tick node. Now, tick node has a few inputs. It takes a uBehavior tree component by reference called owner comp. It also takes an unsigned int 8 pointer called node memory. And it also takes a float called delta seconds. We could call it delta time if we wanted. And this is an override. So we have access to some information here. So why don't we go ahead and generate the definition. We'll go ahead and let our super call to tick node exist here. And here we can do anything we like. And we also have access to things on this service, as services are often used on a behavior tree. And the behavior tree component that owns this node has its own owner. We can access the actor and the controller that owns this particular node. How do we access that? Well, first of all, let's go to uBT service blueprint base, and let's check out the definition. I'm going to go to the declaration here in the H file and scroll down a bit and notice that in the protected section, we have an AI owner. And notice that this is an AI controller. So we have access to that controller. We also have an actor owner of type actor, and we can see what these values are. So why don't we access these, and just to prove that this tick node function is being called, we can add a debug message. So what I'd like to do is take my AI owner, we have access to that, and call get name. And I'd like to just print the name of the owner. So I'm going to use gengine. And let's add on-screen debug message. For the key, I'm going to use 1. Time to display, I'll use 1 second. fcolor can be red. And the string is going to simply be AI owner get name. So I'm going to cut that, use an asterisk, and pass in AI owner get name. Now we see that AI controller is incomplete. And if I hit shift twice and type AI controller, we'll see that that exists in AI controller.h. And we can go there. We can see by hovering over the tab, it's in AI module, classes, AI controller.h. So I can include the header for that, include AI controller.h. So that's no longer an incomplete type. So I'd like to show the name of the AI owner. That should be a controller. I'm also going to show the name of the actor owner. I'll use a key of 2 for this one. I'll use green for the color. And instead of AI owner, we're going to use actor owner. We'll print the name of that as well. So now that we've created a C++ class Let's go ahead and run in debug mode. Okay, so I'm going to go ahead and open up my Blackboard. But before going into my behavior tree and using my service, I'd like to make a blueprint based on it. So I'm going to go into Blueprints, AI, right-click here, and make a new blueprint class based on my custom service, which I called BT service underscore find nearest player. I'm going to select that and call this BT service underscore find nearest player. And if we like, we could just call it BTS find nearest player, so it's not so long of a name. We can double click that and open it, and here's our event graph. And we have functions we can override. So we have things like receive activation AI, and several others, including receive tick and receive tick AI. So those are events that get executed here in the blueprint. And of course, we can add more functionality here in the blueprint if we like. Notice here in the right, we have a custom description and a node name that we can set on this node. And this is going to affect what we see in the behavior tree. We also have an interval. This is how often it's going to tick. It's set to 0.5, but there's a random deviation here. It can be 0.5 plus or minus 0.1 seconds, and we can change that as well. Now, if we set a node name here, such as find nearest player, then that's going to determine the node's name if we add it to our behavior tree. Say we want to attach it to our selector. Now, we can attach it to our selector by right-clicking, going to Add Service, and we now have two new options, Find Nearest Player and BTS Find Nearest Player. BTS Find Nearest Player is the blueprint version. Find Nearest Player is the C++ version. Notice that it took that BT service underscore out of the name. Now let's use the blueprint version BTS Find Nearest Player, and notice that it says Find Nearest Player. If we were to go back into our blueprint and remove this node name and change this to, say, just Find Player and compile and save, then back here we see node name Find Player, but it's not going to show up until we click on it and change it here. But of course, we could select Find Player and hit the delete key and remove it, and right-click and add it back, BTS Find Nearest Player, and it'll come in with that name. Now, we're going to rename this to Find Nearest Player. Okay, so now that we have this, I'm going to go ahead and remove the node and add it again, BTS Find Nearest Player, and it has the correct name. Now, clicking on Find Nearest Player and selecting it, we see its properties exposed to the Details panel, and that includes its interval here. Now, it's set to 0.5, plus or minus 0.1 seconds. That's how often it's going to tick. That's how often we should see our on-screen debug messages. So why don't we test this out? I'm going to press play, and we don't see anything. Let's see what happens if we go into BTS Find Nearest Player and override one of these tick functions. Now we have receive tick and receive tick AI. Because this is an AI character, we're going to use AI. And we're going to drag off of this. Let's do a print string node. It just says hello. Compile, press play, and here we have hello being called, along with, now look at that, our C++ functionality being called as well. And we have Aura AI controller and Aura AI controller. So as we can see, both the AI owner and the owner actor are the controller. And that's because this is the owner of the behavior tree component, not the behavior tree itself. So in our case, they're the same actor. So it doesn't really matter which one we access. In our case, they're both the same. So we see that we have to have event receive tick AI here in order to get that tick node ticking. We'll see that even if we have nothing connected, as long as we have the node, then we'll get that functionality from the C++ side. And this is a nice way to optimize periodic behavior for our AI, because this is ticking every half second. That's actually really slow compared to a regular tick function that would be executing every frame, for instance. Yet, every 0.5 seconds is fast enough for certain things, like finding the nearest player. So our next steps are to actually find the nearest player in this tick node function on our behavior tree service. We want to actually find the nearest player and get some information such as how close that player is and so on. So we'll handle that in the next video. So great job, and I'll see you soon.